So today we're going to have a walkthrough of the code for the Hacky monitor. It's still a bit in progress, but I think it's worth having a look at the moment and seeing where we are and some of the things I've been thinking about. So we're just going to work through literally section by section and just point out some of it. So just there are some print line statements in there, so just to easily toggle those on and off, got a debug statement there. I use a number of standard libraries, as you can see there, for things like the loops and setting up various bits and pieces. So we won't dwell on those, really haven't dug into those too much. The next section is around just really setting up for the OLED screen. I could use a different screen and just change those settings. Because it's an I2C device, you can see they're defining the address. For the external ADC device, I'm using at the moment the Adafruit library. There are a number of libraries available to do that, but in this case I've just stuck with the Adafruit. It works well enough, although if you dig into it, there's some improvements possible, but I haven't really bothered with those. There's a few variable setups here. You can see really just it's a 4-channel ADC, so it's a variable for each of those channels. One of the things, because we're using the WCS current sensor, is as well as a normalized value, which I'll come on to when we get further down, there's an offset as well. So essentially we measure the quiescent current and use that to normalize the value, but we'll see that when we dig into the various areas. And I've got a wait timer that I use. At the moment it's set for 3 seconds, so when the device starts up it waits 3 seconds, just really, especially with this application, things like the speed controllers have a lot of capacitors in there. So I really just want to let those charge, everything settle, measure the quiescent, and then I can use that for the calculations later. There's quite a chunky section here for the WCS, and let's just talk about that a little bit. So you can get these in various different flavors. I'm using this one at the moment, but I could use a variety of others depending on the level of amp range I want and the level of ultimately resolution I'm looking for. So here's one of the key things. So it's 33 millivolts per amp and it's bidirectional. So to get a full range, it's actually 4.62 volts on a 5 volt supply. And you can set, because I'm using an external ADC, I can set the level of gain. I've set it to 4 volts in this case, and it's plus or minus, so it's really an 8 volt range. And what you can see here, this is the key part, is 1 bit is 0.125 millivolts. So just converting that into essentially bits per amp, I know you get 264 bits per amp, and I use that, as I mentioned, I take the ADC value, take away that quiescent current value, divide by 264, and then that gives me essentially my current from using the WCS current sensor along with the external ADC. I've got a external temperature sensor, again just a very simple, very standard DS18B20, used in lots of applications, and just setting it up there so that it's available later on. Here we've got just variables for current sensor. So that's my adjustment. I keep two others here. You can see there's a sort of instantaneous value. So that's really the current at the moment. Peak is the maximum instantaneous value I've seen. An average is a rolling average, and we'll look at how that's calculated a little bit later on. And also, because of the application, there is a 30 amp fuse in the power line. The Arduino is taking its power before then onto a much smaller fuse, but I do want to record if there's a loss of that fuse, so it blows, what was the current at that time, and make it available so I can display it on the OLED screen. And just as mentioned, there's the calculations for the averaging out. So this is the array for averaging, and I use that method for both the current and the temperature, and it's a last in first out, so it's a rolling average over time. Could do other things as well with it, but I just thought for now keep it simple. I can always easily adjust it later on. I want to be able to record when and if the fuse blows, and to do that I need to understand what the battery packs are. So I'm using a 12S battery pack, so 12 cells in a LiPo, and that LiPo will vary between, at the lower range, 3.2 volts up to a sort of 4.2. And I could just pick a value out of there, but I thought this would be a bit more exacting if I took this route. I'm using a voltage divider, as you can see there, 10 and 100K, because the VDD is 5 volts, and if you are running at your highest voltage on the LiPos, you're just over 50 volts. So I need to bring that down to an acceptable range, so I'm not over range on the ADC. If I'm over range on the ADC, then you can blow them according to the data sheet. Don't want to do that. So I'm using a fairly simple voltage divider, and by doing that, you can see here is if I go for the 3.2 as the lowest nominal, what I expect a reading of is roughly just over 45,000. So I've set my lower voltage threshold at 40,000, so that if I see a value less than that, then I'm going to assume that the fuse is blown, and I'm going to record that as in the current fuse loss, what you see there, and also do the same with the temperature reading as well. I mentioned that the temperature sensors use pretty much the same. So again, this is the reading from the sensor, you can see there, and again, what's the instantaneous temperature, peak temperature, average, loss of fuse temperature, and the indexes for the rolling average and the array for the rolling average there. Just a setup for the indicator LEDs, just so it's nice and simple while you're driving. And what I've done here is I've set a couple of limits so that if I go above these, so if I see over 40 amps, I'll turn on one LED, get my teeth in. If I go above 50 degrees centigrade, I'll turn on the temperature LED. Now, I have thought about whether I should reset these if they drop below that limit. Perhaps a better way would be to build in some hysteresis. I haven't done that yet, but it's simple enough to do. Just setting up the encoder, I'm using the encoder on pin 3 and the ADC alert on pin 2, and those are the two interrupt pins available on the Nano. I'm not actually using the interrupts at the moment for the ADC, but I wanted to wire it in a way that I could do in the future. I have tried the encoder without being on interrupts, and it's pretty rubbish. It misses lots. It eventually spots it, but because it's in the main loop, I wanted to remove it, and there was a good tutorial there on what I used to help me set that up. Finally, I'm actually using task loops to do three things: measure the temperature, measure the display, measure the ADC. So the display doesn't have to be updated as frequently as pulling in the readings. I want the ADC to be read the most frequently. It's going to have the quickest rate of change. The temperature, there's quite a lot of essentially temperature inertia, if you like. There's a lot of wiring that the temperature reading, so I'm not expecting the temperature to change as quickly as the current reading. Right, let's just have a look now into the setup loop. And it's a little bit busy. So set it up to for anything going to the serial port fairly quickly. And I just print a statement. It just allows me to spot it after I've done a number of readings. Set up the indicator LEDs, and at this point I switch them on because it's a good visual indicator for two things. One, if they're working, and two, it also shows me that it's going to be doing the reading 0. And at this point I also display the reading 0 on the OLED, and I'm using a couple of different font sizes just so it's nice and clear what's happening at that point. And I also just do a fairly standard find the external ADC. Now, it should never not find it, but from a debug point of view, it's helpful. Notice also I haven't got a sort of debug statement around there. It'd be easy enough to do that. I just haven't bothered in this case. Here, I'm setting the gain. We mentioned that right at the start, so we've got the gain matching the range that I want to be reading, and also the number of samples per second, and that's 32 samples per second, which is still much faster than I'm looking to loop around. You can also set the ADC to read in continuous mode and use the interrupts. This is one of the things that I don't think the Adafruit library seem very good at, and I need to do a bit more. There's a few things on the forum about it, but hence I might in the future change the library and play around with it, but for the moment it's working well enough to get to this stage. Delay the current 0 measurement time. That's really just that sort of 3 seconds, just to delay that out. And then just a bit of clutter that I've commented out, but it's there if I need to. It's just easy enough to show some of the values that I'm reading. And I was also at this stage initializing the array from the first current reading. A reason for that is it just gets you to a rolling average quicker, but honestly it's not necessary in this use case, so I haven't bothered with that. Switch on the sensors, request the sensor temperature, and then read the temperature sensor. And for the temperature, I poked it into the array, so you can see either way works. As I say, it's still a bit of work in progress, but you get the sense of some of the things you can do. This does just get you to that value quicker. Just setting the ADC, which is pin 2, as an input, and if I was setting this as an interrupt, I'd have to attach it and say it's to the interrupt handling routine. and in this case setting it to falling. Set up the encoder inputs, just get where it is at the moment, where it is currently, and in this case I am using the interrupts for the encoder, and we'll see that later on. So those are attached there. What I did mention is I'm using the timer, so I want to kick off those timers, and they're all staggered, so kick those off, kick off the set 0, so I want to read that quiescent current, and just for indication I put it into the serial monitor for a bit of debug. And then now I've got that 0 current, I will just switch the LEDs off, so I've got that all ready and waiting for me. So that's really the setup routine. Here's the loop, and the loop is quite short, really. This is commented out. So the loop timer gives you a value of how long it takes to get around the loop, which can be quite instructive. It takes longer than you think, so that's something to look at as you're trying to make the code more efficient. But in this case, I don't want it running all the time, so I've just taken it out, but it has given me an indication of that loop. And so first block is about if the temperature delay timer has finished, then I'm going to read it. I'm going to average that by calling a routine, and if the temperature peak has changed so that the current instantaneous value is bigger than the previous temperature peak, I'm going to set the peak value from there. I'm going to kick the starter off again. So that's all set, all going. You see here that I'm essentially, rather than going to a routine and reading the sensor, I'm just calling it directly in the loop. And then again, for the ADC, so I'll read the ADC, I'll normalize it by taking off the offset. What I've tried to do here is keep these as integers, so anything that is, so it's still 16 bits, and I think it's an 8-bit processor, but it's better than trying to handle everything in floats, that's for sure. You do then hit the floats at this point, where you have to convert the normalized value into the instantaneous value. So essentially adjusting for the type of sensor you've got. Again, is the peak over what the previous value was, average it out, and also in this case, if my value that I'm measuring for the fuse is lower than that threshold, then I'm assuming the fuse is blown, so I'm going to record in those two variables what that is, and then off we go again. If I'm over the current or the temperature limits, then I'm going to switch on the LEDs. I'm not bothering at this point in time clearing them. I'm just going to leave them on, play about with that later. Here's really the loop for the OLED display. So I've gathered all the data at this point, and by turning it, I'm going to choose what I'm going to display. So just really the running values, or in this case the instantaneous, the peaks, or the blow, and I'm using the font sizes to help me a little bit just in terms of visibility. It's simple. I'm sure it's a little bit ugly, but it does the job, and it's easy enough just to change and set different use cases. And again, just a bit there for debug if necessary. And now, since I've printed it all out, I'm going to kick off the timer for the display. The update encoder routine is really just looking for those state changes. And as I say, I used really an example piece of code to do that. It works well enough. And yeah, it just allows me to use a single interrupt and read the encoder value. Lots of examples of how to do that and how to fully optimize that. But in the case of this application, the encoder is not really critical. So yes, it's a bit of a pain if you turn it and it doesn't necessarily click onto the next display, but you can just turn it again, it will get there. So less worried about absolute encoder accuracy for this application. The average current, average temperature routines are pretty much the same. There's no real significant difference between them, apart from obviously one's current and one's temperature. So we've got an average value there, just as a value within the routine. And what I do here is take the last total and take the last value I put into the array off there, and then I replace that by the current instantaneous value, and then just add that into the running total and increment the index. If the index has gone over the number of readings and it was set around 10, then I just reset that. So you just got this rolling average and return the current average as a float. Same with temperature, so pretty simple. The set 0 is, again, quite a simple routine. I just read a bunch of readings set by the number of iterations, in this case 10. So I run that, I then average those out. There's a short delay, so just try and build in a buffer, so I'm not reading the same value all the time. And then just work out the offset. Again, that's an integer for that. Set the current 0 to that, and that's it. Final bit is just a couple of routines for the display. One just takes in and just for formatting, keeping it simple. And I use those up the top for when I'm printing out from the encoder with different values, and that just simplifies some of that repetitive formatting. So that's for code as it stands at the moment, and it's working well enough. It's working to a point where I'm satisfied to build out a board, blow it in, and do some vehicle testing. And at that point, I'll be able to decide what to do next. It's up on GitHub as well, so if anybody really fancies it, then I'll put the link in the description so you can pull it down and have a look and have a play.